single proportion test. Next problem, right? A manufacturer claimed that at least 98% of the steel pipes which he supplied to a factory conformed to specification, right? An examination of a sample of 500 pieces of pipes revealed that 30 were defective. Test this claim at a significance level of first one 0.5% level, second one 0.01, that is 1% level. Given sample, right? Sample, an examination of sample of 50 pipes, right? So 50 pieces of pipes. So given small n is equal to sample size, that is 500. Let x be the number of pipes in the specification. Given that, right, out of 500 pipes 30 are defective, right? So they have given defective pipes, but x is the good pipes, that is the pipes are within specification, right? Because the manufacturer claimed that at least 98% the pipe is supplying, right, are within the specifications, right? That is what he is confirming, that is he is claiming. So that is why we are taking x be the number of pipes in the specification, but they have given defective pipes. So 500 out of 500 pipes 30 are defective. So the pipes are in specification 500 minus 30, so 470, that is the success here, right? So the sample proportion small p is equal to x by n. So 470 by 500, 0.94. Then q is equal to 1 minus p, so 1 minus 0.94, that is equal to 0.06, right? Now we are going to defining the hypothesis. Null hypothesis: 98% of the steel pipes are within the specification, right? That is population proportion p is equal to 98%, capital P, right? That is 0.98. Alternate type hypothesis, that is not equal to 0.98. So that is population proportion not equal to 0.98. So this is two-tailed, right? Or you can take less than that one. So he claimed 98%, but the specification is the pipes, number of pipes within the specification is less than 98%. You can take like that. So you can use that test also. That is left tail, right? P less than 0.98, right? So q is equal to 1 minus p, that is equal to 1 minus 0.98, that is equal to 0.02. Now test statistics: z is equal to small p minus capital B by p by root of pq by n. So 0.94 minus 0.98, root of 0.98 into 0.02 by 500. So you will get minus 6.3898. So calculated value, take the modulus value. So modulus of minus 6.3898, that is equal to 6.3898. So tabulated value at 5% level, we know 1.96 for two-tailed. So conclusion: calculated is greater than tabulated, therefore H0 is rejected. So it is not true. That is 98% of the steel pipes within the specification, right? Manufacturer claim is rejected. So 98% of steel pipes are not in specification, right? Not at least 98%, right? Then maybe less than that. That is what. Next, you take the 1% level. 1% level tabulated value is 2.58. So conclusion: here also the calculated value is greater than tabulated value. Therefore, H0 is rejected. Next problem. 24 dice are thrown in 1543 times, 1543 times, and a throw of 3 or 4 or 5 reckoned as a success. So getting 3, 4 or 5 is a success, consider as a success. Suppose that 19,142 times 3, 4 or 5 have been made. do you think that observed value deviated from the expected value significantly, right? So given 24 dice are thrown in 1543 times, that is, a die is thrown 24 into 1543 times, both are same. So if you are throwing a 24 dice or a die 24 times, both are same. So a die is thrown in 24 into 1543 times, right? So 37,032, right, times. Sample size n is equal to 37,032, right? Here getting 3 or 4 or 5 is a success. So the probability of success P is equal to probability of getting 3 or 4 or 5. So we know that is a probability of getting 3, all are independent, right, events. That is why probability of getting 3 plus probability of getting 4, probability of getting 5. 1 by 6, 1 by 6, 1 by 6 we know, right? 3 by 6, that is equal to 1 by 2. So P is equal to 1 by 2. Q is equal to 1 minus P, that is also 1 by 2. So right, so I already told you, whenever you are taking coins or these dice, you need to go through binomial Bernoulli idea, right? So expected number of success E of x NP, right, we know from the binomial, right? 37,032 into 1 by 2, so 18,516. Given observed success is 19,142, that is x. So define hypothesis. Null hypothesis, there is no significant difference between observed and expected value. Alternate hypothesis, there is a significant difference, right? So test statistics is equal to x minus np by root of npq, right? Np mean root of npq variance, binomial, right? So 19,142 minus 18,516 root of 37,032 into 1 by 2 into 1 by 2. So you will get 6.5060. So we know that in all probability value is z is equal to 3, right? Z less than or equal to 3. So we are taking the maximum value z is equal to 3. So conclusion, calculated value is greater than tabulated, therefore H0 is rejected. So there is significant difference, right? H1 is accepted, right? H0 is rejected. Next problem. When you're tossing a coin 100 times, a boy gets heads 66 times. Do you think that the coin is unbiased, right? Given sample, how many times? 100 times. So n is equal to 100. Getting a head is a success. So P is equal to probability of getting a head, that is 1 by 2, right? So Q is equal to 1 minus P, that is also 1 by 2. Here we are using binomial, right? Expected value of success E of x is equal to NP, that is equal to 100 into 1 by 2, 50. Observed heads, number of success, that is x is equal to 66. So defining the hypothesis, null hypothesis, the coin is unbiased. Alternate hypothesis, the coin is biased, right? So test statistics is equal to x minus np by root npq, 66 minus 50 by root of 100 into 1 by 2 into 1 by 2. So you will get 3.2. We know in all probability standard normal variate lie between plus or minus 3. So we are taking plus 3. So z is equal to 3, that is the maximum. So conclusion, calculated value 3.2, which is greater than tabulated value, therefore H0 is rejected. So coin is biased. Thanks.